So we're going to talk more about complex shapes. So we're talking about more complex shapes to get into the effect of weight. But even for something like a teardrop shape with almost no weight, there's still much more complex interactions going on around that shape than for the flat plate. And so in the case of a nice teardrop shape, you can come up with an analytical solution. It is still a little bit more complex. So we typically describe the coefficient of drag. So we're typically going to use the coefficient of drag to describe more complex kind of real world shapes. We're going to say the drag force is 1/2 rho times CD times the area times the velocity squared. And this is some data now on what coefficient of drag looks like as a function of Reynolds number for a number of different shapes. So this bottom curve here, that's a smooth flat plate parallel to stream. That's that relationship from the Laplacian solution that we derived for the drag coefficient on a laminar for a laminar boundary layer around a flat plate. This is what happens during transition into turbulence. We also looked at some relationships for flat plates based on that. And then up above, we have all of these other kinds of shapes, right, including like an airfoil, a pigeon, a seagull, a sailplane, which are all fairly aerodynamic, and then some smooth circular cylinders and square cylinder up above.
So we know that a pigeon is more has a lower coefficient of drag than a square cylinder.
Yeah, so a pigeon is more aerodynamic than a square cylinder.
Good stuff.
That's good to know. You remember one thing for this class, that would be the pigeon is more aerodynamic than a square.
I will write that on the exam.
Extra credits.
Oh man.
What about the difference between a European and African swallow?
Well, we're talking about late. So anyway, this is a more complex relationship, right, than what we had for our smooth flat plate. We don't have an analytical solution, an exact analytical solution for like what's going on around a square cylinder. And so experimental data is going to be your friend here, right? It's another place where we're going to be looking up numbers that we use essentially as part of our solution. One thing to note, though, is that we're going to see area in here. And we talked about this early on in this chapter, but I want to hit this again. There are a few different ways to define area. So it could be the planform area, and that would be like what's denoted here is AW or wing area. It's like the area as you're looking down on the object. So it's like the area of the body as seen from the top. It could also be the frontal area, which would be like the area of the body as seen from the front. So this is a projection now of this airplane. We're looking at it from the front, and that's the frontal area. Sometimes you'll also see wetted area. We're talking about a surface ship, talking about a ship traveling through the water. We'll talk about wetted area, which is like the area of the hull as it's moving down downstream. So for drag coefficients, when you see CD, right, you see a plot like this. Most of the time for a drag coefficient, the area the relevant area you use is this frontal area. Like the area if you project it backwards. For a sphere, it doesn't matter, right? For a sphere, the frontal area and the planform area, whatever, is the same. The wetted area would be different for a sphere, right? That'd be the surface area. The frontal area and planform area for a sphere would be the same. It'd also be the same if you had like a cube, right? We're comparing to a pigeon or something. But a pigeon would not be the same, right? A pigeon would have different frontal area and planform area. So for drag, we're most often concerned with frontal area. This frontal area is what determines or has a more direct relationship to the wake behind the object. Right? In some sense, the size of the wake, we increase the size of the frontal area of an object, we're also going to increase the size of the wake. And the wake is one of the most important contributions of drag around real objects, particularly with blood-shaped objects like a square cylinder or a sphere. But that's not always true. So you have to be careful. And you have to know before you're using coefficient of drag to figure out the drag force, you have to make sure you're using the right area. Okay. So actually, I should have labeled this with which area this is. I assume, actually, I'm not sure what area that is, or is that CD. That might actually be platform, but I would have to look that up before I would use it. Let's say to solve the problem. So now we talked about this in the video today, but we can generally think of there being two components to drag: friction drag and pressure drag. So we could actually take our coefficient of drag. We don't typically do this. Typically, we just look at a single number for a given shape. But we could think of it as being split into a coefficient of drag due to friction, skin friction, and a coefficient of drag due to pressure, right, or weight. So in the case of a sphere, for example, this is like the skin friction drag in that boundary layer towards the front of the sphere, and this is the pressure drag due to the size of the weight between the front and causing a pressure difference between the front and the back of the sphere. So pressure drag becomes dominant for blunt bodies because of the weight. So this is some data for this kind of standard shape, not quite a teardrop, but essentially it's a circular shape, half circle in the front, tapered out in the back. Right? And if you imagine taking that object and increasing the ratio of the thickness of the object, right, the width of it going into the stream relative to its length, at zero thickness, basically just a flat plate. At zero thickness, we basically have just a flat plate. And then as we increase the thickness of the object, we're going to see a, this is the percentage of drag, which is due, this should have been labeled better. This is the percentage of drag that's due to skin friction. And so as we, so this isn't showing total drag force, it's just percentage of drag. As we increase the thickness of this object, the weight gets bigger and bigger, and therefore has a bigger contribution to the overall drag on the object. To the point where by the time we get to a really, an object that's really large relative to its length, then it's almost all pressure drag, almost no skin friction drag. Make sense? Good question. My guess is the question is what is a 3? I'm guessing that that's because it's bad problem on my part from the. I need to look at that.
I don't know if that looks like you said the 3%.
Yeah, no, I don't think that's. I think that's. This comes from the text. Pretty sure it's probably down in the text. But I will check on that. And it would be in the updated slides by the end. Anyway, so you can see that as we get to objects that have. So this just goes to T over C of 1, right? And at that point, we have most of the drag is pressure drag. Right? So the sphere, it's a different shape at the back. The T over C is roughly 1, and most of the drag is pressure drag. Wouldn't have exactly the same shape. So, so this means that streamlining. So to get to average question, streamlining can have a huge impact on drag coefficients. So this shows two different objects. One just like a rectangle, and the other this kind of like bullet-shaped thing. And they have the same frontal area, but if we take off these corners, we see the coefficient of drag here is 2. The coefficient of drag here is 1.1. Right, so nearly just by, so we haven't done anything like maybe teardrop shape in the back or anything. All that's happened here is that we reduce the just lop off those front corners, and therefore get a very, very different coefficient of drag. So in this case, you can see they're kind of schematically showing that we get these kind of vortices forming off of those front corners, which increase the effective size of the wake of this object pretty dramatically. And by just blocking off those corners, you reduce the size of the wake, you get very different coefficient of drag. This one's pretty dramatic. This is, these two objects have the same drag force. So this is like a small little sphere, or a small little cylinder, versus this giant shape. These both, this would be to scale relative to each other. This thing would have the same drag force as this, just because of the effect of streamlining and the reduction of weight. Kind of schematically shown here, they have similar kind of weight sizes, even though this one.
What exactly is streamlining?
For example, like the Wright brothers Wright Flyer, one of the biggest things they could have done to improve the performance of the Wright Flyer, it used wings that were made of fabric that was like cable stayed, basically like what you would do in a sailboat. But all of those cables, like each one of those cables is a little cylinder. And so each one of those cables has the same amount of drag force. If you use the same amount of drag force as this enormous thing hanging out, that would be hanging out. And you wouldn't design an airplane with like these big, enormous, big, enormous struts that look like this running all over the place. You see a picture of the Wright Flyer, there's cables running everywhere. But all of those things have enormous, actually, contributions to drag force. So cylinders are actually pretty bad for drag force. So streamlining can have a huge impact. There are many experimental drag coefficients given in your text and other resources, right? This is a thing you will often see recorded when people are talking about drag. So here, this is nice. It says CD based on frontal area. So we know what area we're talking about, and we're looking things up in this table. We see a cube, it's oriented flat side on versus corner on. Goes from 1.07 to 0.81. This cup shape, right, depending on how we orient it, has a huge impact on drag, and so on. So that's for coefficient of drag. Sometimes, though, you'll often see drag recorded as CDA. So if you look down here, here's for a person on a bicycle. You'll see upright CDA 0.51 square meters, racing CDA 0.3 square meters. So for complex objects, like let's say we're measuring someone on a bicycle in a wind tunnel, we want to know, we want to be able to predict the drag force on the person on a bicycle. Like someone sitting upright versus someone sitting down really low is going to have both a different coefficient of drag because they have different shape, and also a different area. Those two things are tied up together. It's kind of hard to disentangle one from the other. And so in that case, you'll often see this recorded as a CDA, which is coefficient of drag times area. And so to use that, you just replace the entire CDA in, so that would be this entire CD times A within our expression for drag force. Okay. Then you just multiply CDA to 1/2 rho squared to get the overall net drag.
What is the T over C?
Yeah, T over C is the ratio of the thickness to the length. C would be here is chord length, like how long that is. So, and here are just some examples for low drag cars. And you can see most of these are electric cars with super low coefficient of drag, about 0.2. Because if you have range is one of your primary concerns, one of your primary concerns, and you really want to reduce coefficient of drag as much as possible. And the Tesla does really well. And I thought this was interesting. This is the plot of drag coefficient versus like rough production year. And you can also see this nice trend from big boxy shapes to things that are much more streamlined. It's just an engineering stuff. Should get better now. And a steady reduction in CDA. Yeah. right? With that, an increase in fuel efficiency is